Welcome, everyone. It's a great pleasure to have Zheng Zhou as our speaker today. Zheng is a PhD student at the Perimeter Institute for Theoretical Physics. Uh, Although Zheng is still at a very young stage, he has done a lot of interesting work, in particular in conformal field theories. But now he is one of the pioneers who uses the fuzzy sphere technique to study three-dimensional, 2+1 dimensional conformal field theories. And I think today he will give us some summary of this direction of research. John, please go ahead.
Okay, good morning, everyone, and thank Liu Jun for inviting me for speaking here. So today I'm going to talk about how we use the fuzzy sphere to study the 3D CFTs. So first, I will make a brief introduction to the 3D CFTs. After that, I will mainly talk about two directions. The first is to use fuzzy sphere to study the critical gauge theories. This includes the Chern-Simons matter theory and the deconfined criticality. After that, I'll move on to introducing about the conformal defects and boundaries. So as a brief introduction, conformal field theory has been one of the central topics of modern theoretical physics. In condensed matter, it is used to describe the critical behavior. In high energy, for example, in string theory, it is used to describe the 2D world sheets. Moreover, it reveals some fundamental structure of the quantum field theories, for example, the renormalization group flow. So focusing on the critical behavior aspect. So one of the simplest example of a quantum phase transition is in the quantum Ising model, where by tuning the transverse field, there will be a quantum critical point that spontaneously break the Z2 symmetry. So if we consider the space-time symmetry, in the UV, in the microscopic model, it is very small. It is the discrete space translation and rotation and the time translation. But at the quantum critical point, in the infrared or in low energy or long wavelength, there will be a very large emergent conformal symmetry generated by translation, rotation, dilatation, and special conformal transformation. These symmetries form a group of SOD plus 1, comma 1. These symmetries, in return, cast very strong constraint on the operators. For example, each operator must carry a certain Lorentz spin under the SOD rotation or a scaling dimension under dilatation. Moreover, the SCT singles out a special kind of operator called the primaries, which are invariant under the special conformal transformation. The 2-point and 3-point functions of these primaries are fixed to be some kind of power law, and the power is determined by the scaling dimensions of the operators. In the context of phase transitions, the scaling dimensions also gives us the critical exponent. For example, in 3D Ising model, most of the critical exponents are given by the scaling dimension of two lowest operators, the Z2 even epsilon and the Z2 odd sigma. So the conformal symmetry is very powerful. In 2D, and besides those global conformal symmetry, there exists an infinite dimensional algebra called the Virasoro algebra, which leads to many exactly solvable rational theories. In 3D, although the CFTs are not exactly solvable, the conformal bootstrap still casts very rigorous bound on the scaling dimensions. For example, for the Ising model, it can determine the scaling dimensions up to 6 or 7 digits. So besides these well-studied theories, people are devoted to explore new, more interesting theories. For example, one of the pioneering example is the deconfined criticality, which is first proposed to describe a direct phase transition between the Néel and VBS order. It is the phase transition between two different ordered phases, so it goes beyond the Landau paradigm. later people find out something more interesting about it. At the critical point, there is an emergent SO5 symmetry with 3 components coming from nail and 2 components coming from VBS. So being different from an ordinary SO5, say SO5 Wilson-Fisher, this SO5 is known to be anomalous. Colloquially, each U1 flux of the VBS autoparameter captures an SO3 spin half. So this deconfined criticality is known to have many dual descriptions. For example, there is the scalar QED with 2 flavors of bosons, or SU2 QCD with 2 flavors of fermions. So if we look closer at these descriptions, one common thing is that they are constructed using the gauge fields. So the gauge theories are among one of the few known ways to construct interacting 3D CFTs. It also gives rise to many interesting problems. For example, condensed matter people are interested in the nature of direct spin liquid or the nature of the CPN theory. In higher energy, there is also the significant problem of the conformal window of the gauge theories. So to make things even more interesting, we can add some non-trivial dynamics to the gauge field. That is the Chern-Simons term. And this altogether will give us the Chern-Simons matter theory. And those theories describe transitions between different topological orders. Moreover, they also host dualities between different interacting theories. Recently, people have also found that these theories are very experimentally relevant. And they describe transitions in fractional quantum Hall systems or Moiré systems like twisted bilayer graphene or twisted bilayer TMD. But these theories are very difficult to study. For conformal bootstrap, for example, they cannot distinguish different theories with the same global symmetry. For quantum Monte Carlo, there is inevitably the sign problem. So that's why we turn to another recently developed the method to study the 3D CFTs called the fuzzy sphere. So the fuzzy sphere studies the electrons moving on a sphere with a magnetic monopole at its center. So it is first applied to the 3D Ising CFT and have been proven to be very powerful. And using fuzzy sphere, a very wide range of spectrum can be obtained at a very high accuracy on even very small system size. For example, at the size of 16 spins, the error compared with the bootstrap is already within 1%. Moreover, it's the first numerical verification of the conformal symmetry in the 3D Ising transition. So to better explain the idea of fuzzy sphere, we split it into 2 keywords. So sphere, we want to put a quantum Hamiltonian on a sphere SD. This is because considering the imaginary time in direction, this forms a generalized cylinder S2 times R. So this manifold is known to be conformally flat. That is to say, through a conformal transformation called the Weyl transformation, it can be transformed into a flat spacetime. So each time slice in the cylinder is transformed into a concentric sphere. So because of this property, we can use some very nice properties of CFTs on the flat spacetime, one of which is the state operator correspondence. This says that each CFT operator has a corresponding eigenstate of the quantum Hamiltonian on the sphere. So the state and the operator has corresponding angular momenta, corresponding quantum numbers under global symmetry. And moreover, because the Hamiltonian, which translates one time slice into another, get transformed into the dilatation operator, which sends one concentric sphere to another. Their eigenvalues, the energy, is now proportional to the scaling dimension. That is to say, the excited energy of an eigenstate is just off by a constant factor with the scaling dimension of the CFT operator. Using this property, we no longer need to do very complicated finite size scaling to obtain the scaling critical exponents. We just need to read it off from the energy spectrum. So to put quantum Hamiltonians on a sphere, in 1 plus 1D, things are very easy. One just need to consider a lattice chain with periodic boundary conditions. But in 2 plus 1D, things get a bit harder as there is no lattice that preserves the full SO3 rotation symmetry due to the curvature. So that's why instead of the lattice, we use the spherical Landau levels as the single particle state to regularize the QFT. So specifically, we consider the electrons moving on a sphere with a magnetic monopole at its center. And the magnetic flux will modify the single particle Hamiltonian and further modify the single particle eigenstates. Now, the single particle eigenstates form the highly degenerate spherical Landau level. For example, the lowest Landau level has a degeneracy of 2s plus 1, and then 2s plus 3, etc., etc. So if we set the single particle gap to be much larger than the so if we set the single particle gap to be much larger than the interacting Hamiltonian, and if we partially fill the lowest Landau level, we can constrain the fluctuation within the lowest Landau level, or to project the system onto the lowest Landau level. So now we have the single particle states. We need to construct the interacting Hamiltonian. The building block we use is the local fermion bilinear, or what we call the density operator, with a matrix insertion to put it on some representation of the global symmetry. So for example, for the Ising CFT, we only need to put a density-density interaction in the z direction and a polarizing term that favors the x direction. So that's how we write down the model to put the simplest Ising theory onto the fuzzy sphere.
Can I ask a very quick question? Sorry, like this is
Yes.
routine. So I have a question about the previous slides. Actually, I missed something that you mentioned, that why dimensionality related to the SO3 rotation. Why do you need SO3 rotation? Can you remind me again?
We need to put a quantum system on a sphere. The sphere naturally owns the SO3 rotation symmetry. And we also want to keep the UV symmetry as large as possible so that its flow to the CFT in the IR is shorter. So we get smaller finite size effect.
So you're saying that in 1D you need S1 and in 2D you need something like S2, something, is it
yes,
right?
Yes, exactly.
Okay, thank you. And the next, about the next slides.
Yes.
I missed a little bit about why, like what is required. Is it like you just need to find something with Ising CFT on the Ising symmetry on the sphere? So you add those terms and try to add the simplest term that has the preserve the Ising symmetry. Is it the idea I should have?
Yes. So the idea is to match the global symmetry as well as the phase diagram. So you see the first term, it favors the ferromagnet, favors the quantum Hall ferromagnet, whereas the second term, it favors a paramagnet. So the transition between where those two terms dominate is a Ising type transition.
I see. So it is to some extent, it's by design to set to fit this setup, and you want to have something that have the Ising transition.
Yes.
Okay, good. Thank you.
Okay.
Hi, excuse me. I also have a question. So how can we determine this density operator for generic CFT? Is there a method?
This density operator is a construction in the microscopic model.
Okay, I see. So
it is just like how you say put a spin on the lattice model. It is some construction in the microscopic model in the UV.
I see. So this is to say, as long as we know the microscopic model, then we know how to write on this density operator.
Basically, the guiding principle of the Hamiltonian design is to match the phase diagram and match the global symmetry.
Okay. Thank you. And I have another question. So why do we focus on the lowest London level? Is it because just for simplicity?
Yes, just for simplicity.
I see. Thank you.
Also, you see those lowest London levels has very nice properties that each orbital is quite localized. Such properties doesn't appear in higher London levels.
Oh, I see. Thanks.
Did you do any experiment on higher nano levels? How bad is it?
Well, with the we have a more systematic way of designing the models called the pseudopotentials. The pseudopotentials actually doesn't quite recognize the lowest Landau level with the higher Landau levels.
Meaning they are the same or?
So far we cannot answer this question quite well.
But can I know why? Because the model look the same or?
Yeah, the model looks the same.
Is
So so by that construction, the only thing you need to know is that the fermions, they live in a spin S representation of the SO3.
But is the fact that the models look the same a coincidence in this particular setup, or what do you think is more general?
It is general in the quantum Hall systems or on the Landau levels. No matter
Let me make sure when you say that they look the same, you mean everything we have to change is just this YSM, right?
yes.
But in principle, for different Landau levels, we have different YSM. Then when we do numerics, maybe the performance will be different.
Somehow you see that the Hilbert space, they are not complete. So it is possible that if you, after the projection, the model can look the same. For example, by fine-tuning, you can, on the lowest Landau level or on the higher Landau levels, you can tune the model to the same. It is just that it is interpreted as different interaction potential.
I see.
Yeah, yeah. But the interpretation on the lowest Landau level shall always be the simplest.
I see. So if just to make sure what you mean by this, do you mean suppose I define any interaction Hamiltonian on one of the many Landau levels, then I can define a different Hamiltonian on another Landau level such that the matrix elements in these two Hamiltonians have one-to-one correspondence.
Yes, basically.
I see. Thank you.
Sorry. Yeah, excuse me. Yeah, I have a trivial question. So you have for the first condition, you have assumed that the H0 is much larger than the interaction part. right?
Yes.
So yeah, I want to ask how can we handle the situation that the interaction term are compatible or even larger than the H0?
Typically we don't deal with those conditions.
So
We just assume that the single particle gap is infinite, so
yeah,
that the electrons cannot hop from the lowest lambda level to the higher lambda level. It is just a consideration by consideration of the model design.
okay. So currently we can only handle the gapped system, right?
Yeah, the system with single particle gap.
Okay. Okay, thank you.
Yeah. It is just because those conditions are enough to produce the physics we want, the
Okay.
IR physics we want.
Okay. Yes, thank you.
So shall I continue? So we have introduced how to put the simplest Ising CFT onto the fuzzy sphere. So moving on to the more complicated cases, for example, the D2CP or the transaminase matter theories. So we make use of a tool called the nonlinear sigma model. So the D2CP is known to be described by a nonlinear sigma model on S4, a four sphere that has coordinates with 5 components and with a level 1 Weiss-Zumino-Witten term. This Weiss-Zumino-Witten term captures the order intertwinement between the NEO and VBS. In other words, it captures the anomaly. So by noticing that the S4 manifold can be written as a Grassmannian SP2 over SP1 times SP1. Here we use the notation that SP1 equals SU2. So we can further generalize this Grassmannian to a more general symplectic Grassmannian, SPn over SPm times SPn minus m. This the nonlinear sigma model on this Grassmannian with a level 1 Weiss-Witten term. This model is known to host many topological orders in its phase diagram and the transaminase matter theories that describes the transition between them. For example, there is n flavor of bosons coupled to SPm or SPn minus m level 1, or the n flavors of fermions coupled to SU2 with the transaminase level. So to realize this nonlinear sigma model with Weiss-Witten term on fuzzy sphere, we begin with constructing an SPn symmetric model. That is to say, we put 2n flavors of fermions on each orbital.
Oh, sorry. Hold on. I don't remember. Can you remind me for SPn over SPm and times SPm minus m for any n and m? Do people know what is the corresponding gauge theory?
These are all these possibilities are what I list here. So
Oh,
here, phi means bosons and psi means fermions.
So for each n and m, there are multiple possibilities for the gauge theories.
Yes, exactly.
Thank you.
So we put 2n flavors on each orbital, and we break the flavor symmetry from the maximal SU2n to an SPn symmetry, and we fill 2m out of 2n flavors. In this way, the SPm and SPn minus m that get modded describes the symmetry of the field and the empty flavors. And the matching of the Weiss-Zumino-Witten term is proven in the SP2 or SO5 case, and we expect the SPN case to be a natural generalization. So more concretely, we construct the interacting Hamiltonian through fermion bilinears. For example, there is an SU2n invariant bilinear psi, dagger psi. We add a density-density interaction, which preserves the SU2n symmetry. And there can be a pairing operator, psi, omega psi, where omega is the symplectic matrix. And this term breaks the SU2n symmetry, but is SPN symmetry, but preserves the SPN symmetry. So we add a pairing interacting term. So this is how we, yes?
Up to cortical term, is this the most generic SPN symmetric interaction?
Yes.
I see.
You can prove that you can exhaust all the so we study this model through a exact diagonalization calculation. So how do we extract the information of the CFT? That is through the state operator correspondence. Remind you that each CFT operator has a corresponding eigenstate on the fuzzy sphere. And they have corresponding symmetry representation. For example, the SO3 3 spin can be measured by the total angular momentum. The SPN flavor can be measured by the SPN quadratic Casimir. And at half filling, there is another particle hole transformation on the fuzzy sphere, which translates into the parity of the CFT operator. More importantly, the scaling dimension is proportional to the excited energy, and the factor alpha between that converts these two values and can be determined by criteria of conformal symmetry. For example, there in a CFT there must be a conserved current with scaling dimension exactly 2, or a stress tensor with scaling dimension exactly 3, or the integer-spaced multiplets. So our first evidence for the conformal symmetry comes from the conformal multiplet. That is to say, starting from a primary phi with scaling dimension, say delta, by acting repeatedly the partial derivatives, spatial derivatives, we get its descendants. For example, we act it once, we get partial phi with scaling dimension exactly 1 higher. And if we add twice, there are two options: either the spin 0 partial square phi, Laplacian phi, or the spin 2 partial phi. And this structure continues on and on infinitely, which forms a tower-like structure. And for spinning primaries, there are also structures that includes the antisymmetric epsilon tensor. So in our model, we find that all the states can be classified into different conformal multiplets, and in the conformal multiplets, it has very good integer spacing. For example, we can look at the lowest operator in the antisymmetric tensor representation, and we can find all of its lowest descendants at very good integer spacing. And for the conserved flavor current, and both structures containing epsilon and not containing epsilon can be found, and and this is very good for SP3 and SP4 as well. So how are we sure that those states that forms the integer spacing are descendants of the same primary? We can make use of the conformal generators. For example, the conformal generator P mu plus K mu can be written as the Hamiltonian density H integrated against the coordinate. So by acting this generator on a state, it increases or decreases the number of partial derivatives by 1. For example, if we act on this phi state, it will give you partial phi, and if you act on the partial phi states, it will either give you the spin 0 component of phi and Laplacian phi, or the spin 2 component of partial mu phi. So we measure the overlap of the states on the left-hand side and the right-hand side. This tells you how much this generator sends the states to what it should be. And the overlaps closer to 1 characterizes better conformal symmetry. And in practice, we find that for these lower values, all of these overlaps are larger than, say, 93 or 95%. And for the lowest ones, it is even better, larger than 99%, which characterizes this good conformal symmetry. So to quantitatively measure the conformal symmetry, we define a cost function which measures the average discrepancy from the conformal symmetry. For example, there can be terms like in this cost function, there can be terms like delta t minus 3 squared, or the delta j minus 2 squared, or the delta partial phi minus delta phi minus 1 squared. So we find that for n larger than 3, there is very small cost function, and as the system size gets larger, it scales towards 0. Whereas for the SP2 case, the cost function is quite large, and it remains quite constant as we increase the system size. This suggests that the SP2 case, which corresponds to the DQCP, is somewhat strange, somewhat different from the prediction of the conformal field theory. Actually, people have found various strange things about deconfined criticality. For example, it's the strange scaling behavior. The scaling dimensions, they drift with the system size, and they violate the bound set by conformal bootstrap. An interesting proposal to reconcile these strange behaviors is the idea of pseudo-criticality. To explain the idea of pseudo-criticality, we put the deconfined criticality into the context of gauge theories. For example, the n-flavor scalar QED. So at large n, this theory is known to be conformal with 2 conformal fixed points, and describe one attractive and one repulsive, describing the scalar QED and the critical QED. So as we decrease n from large n limit, these 2 fixed points get closer and closer, and finally collide into the complex plane. That is to say, there is no fixed point on the real axis, but 2 conjugate fixed points in vicinity of the real axis being complex. So in vicinity of those complex fixed points, the RG flow is very, very slow. And so if the system size is not large enough, the flow will stuck in this working region, and we will observe behaviors that is controlled by the complex fixed point in its vicinity, and that's what we call the pseudo-critical behavior. And in our SP2 model, we indeed approximate conformal symmetry in a wide range of parameters, but not as good as the truly critical cases. And these and to further confirm the scenario of pseudo-criticality, we can look at the RG flow through the lowest singlet that controls this flow. So in the scenario of pseudo-criticality, the RG flow is first attractive and then repulsive. Correspondingly, the singlet is first irrelevant, larger than 3, and as the flow goes, its staining dimension decreases to lower than 3, being relevant. And in the truly critical,
Sorry. What is the horizontal axis?
some tuning parameter.
I mean,
That
this
is
R over R0.
sorry, I missed the last sentence.
The R over R0. That's something.
Oh, here, the system size.
Uh-huh.
So a linear scale. So as the system size increases, it goes from, for example, from this orange arrow to the yellow arrow, and goes on and on.
I see. Mhm.
Okay. So in the pseudo-critical case, the S will flows from slightly irrelevant to slightly relevant, whereas in the true critical case, the flow is first repulsive and then attractive, which means the staining dimension will increase from below 3 to above 3. And in our numerics, we indeed see behavior that is consistent with the scenario on the left. That is to say, the staining dimension of S as the system size increases decrease from above 3 to slightly below 3, which is consistent with the scenario of complex fixed points. So besides this singlet, we can obtain a lot of primaries and their descendants, and many of them play a very important role in the original neo to VBS story. For example, there is the tuning parameter, or the order parameter, or the dangerous irrelevant operators on the Honda and square lattice. So it's not only for the SP2 or SO5's theory. We can also study the operator spectrum of the SPN model. Remind you that it is described by this nonlinear sigma model on a symplectic Grassmannian with a topological term, and it has many candidate gauge theories. Although so far we are not sure which theory we are looking at. So we find that these SPN theories with different feeling, their operator spectrum has many things in common. For example, the lowest operators in the antisymmetric wrap or the spin 4 wrap, their staining dimension is very close. But there are also some different things. For example, there are operators that does not exist in the SP2 theory, but start to show up in the SP3 or the SP4 theory. There are also operators, for example, here, that is their scaling dimensions are very large in the SP4 theory with quarter filling, but turns out to be very small in the SP4 theory with half filling. We can also look at the singlets in that theory. So we find that in all of those theories, the lowest singlet, it has a scaling dimension very close to 3. For the SP3 or SP4 with feeling of 1/3 or 1/4. It is slightly below 3, which means it controls probably controls a phase transition with very slow RG flow. Whereas for the SP4 with half filling, it is slightly above 3, but still all of those are very close to 3. And the second singlet is at slightly above 4. So if we look at the half field theories, the first singlet has parity even, and the second singlet has parity odd, which means very strangely that if they are described by the fermionic description, the parity odd one will be the mass term fermion with 2 fermions, and the parity even one will be the 4 fermion one. It is even lower.
Okay, so 2 questions. First, how do you determine the Weissmuller-Witten level? Just by the Aharov-Wigman calculation?
This calculation has been rigorously done on the SP2 case, and here we think it's a natural generalization.
Okay.
We are trying to repeat that calculation for the square diagram.
Square diagram.
And the square diagram.
Sorry, what's the square diagram?
That is the perturbative calculation that determines the Weissmuller-Witten term.
Okay. But you mean you want to generalize it to larger n and m, or to arbitrary n and m?
Yes.
The other question is, here you mentioned you at the moment you do not know whether which gauge theory this model flows to, but suppose you want to determine it, what would you do?
And we will look at the phase diagram. But here the phase diagram is quite difficult because you see the scaling dimensions are very close to 3. So the flow is very slow. So it is easy to access the transition itself, but hard to access the phases.
But can I simply just do some large N analysis of the gauge theory and just compare the scaling dimensions?
You see here the n is still quite small.
Is 4, yeah, 4 sounds pretty big. 4 may be big.
Okay.
I mean, yeah, it's just a suggestive. It may not be conclusive.
Yeah.
Mhm. But if you want to look at yeah, go ahead.
If you think large n for n equals 4 is convincing enough, that may be a good way to proceed.
Mhm.
But still, I think the
Mhm.
large n calculation here is a bit difficult. Yeah.
And then when you say you want to look at the phase diagram, what exactly do you want to look at?
First, we want to look at whether it's gapped or ordered. That's the first thing. Then we want to determine the nature of the
Oh,
topological order in its vicinity.
I
So
see.
that can be calculated by putting the same model on a torus instead of on a sphere, so that you can look at the topological degeneracy. That is what we are trying to do.
I see. Um, Yeah, this, naively speaking, this doesn't sound too hard, right?
But our system size is very small because we can only access by ED. For example, here, and for the SP3 theory, the best we can do is 7 orbitals combined with 6 flavors. That means 42 sites. So so with 7 orbitals, it's still a quite small system size.
Mhm.
and combined with the fact that the RG flow is very, very slow, that makes determining the nature of the phase quite difficult.
I see. Thank you.
Okay, so making a brief summary, we have studied a series of syncretic CFTs using the fuzzy sphere. We have found the evidence for the conformal symmetry, including the integer-spaced multiplet, the conformal generators, and the cost function. So for SP2, it is the deconfound criticality. We have found evidence for the pseudo-criticality and have obtained a wealth of information from the spectrum. So in the future, we want to observe more directly the complex CFTs by studying a non-Hermitian Hamiltonian, which just can realize the complex CFT, and there can be more convincing confirmations of the direction of the RG flow, for example, through the RG monotonic functions. For SP3 and SP4, they are a series of new unexplored CFTs with candidates being the transaminase matter theory. And although we are not sure which theory what we found correspond to, and we can gain more evidence from the topological orders in its vicinity. And we can take a step back to study some theoretically theoretically simpler theories. For example, the abelian U1 level K coupled to matter theories.
So what do you mean by the last point? How do you study the abelian U1 level K plus matter theories?
We're guessing that we can study them by, for example, breaking the SPN symmetry to a SUN times U1.
And then the CFT you study may naturally flow to this one.
Yes, exactly.
I have another question about the cost function. In the definition of the cost function, you have many terms.
Yes.
But how many? So I guess NST means the number of terms you keep.
Yes. So in practice, what we keep is all the criteria that has scaling dimension lower than 3, all the operators that has scaling dimension lower than 3. Altogether, there are 8 of them, descendants and conserved currents.
I see. Thank you.
Yeah, but we made sure that different choice of the cost function doesn't have have much impact on what we find.
Yeah, thanks.
Yeah, I think the time is quite limited, so let me briefly introduce the conformal defects and boundaries we study.
I don't want to really put any cutoff. So if you wish, you can take as much time as you want.
Okay. Thank you. So defects and boundaries are very important objects in theoretical physics. For example, the line defect, it is a space-time dimension 1 object. And it can correspond to impurities together with the time evolution direction. For example, the famous Kondo problem. In quantum field theories, it can also correspond to the line operators. For example, the Wilson line or Truth line in gauge theories, they are also line defects. On the other hand, boundaries, they are space-time codimension 1 objects. And they are everywhere where in experiments and in daily life as our samples are finite. They can also tell you very non-trivial things about bulk. For example, there is the famous ADS-CFT correspondence. So more specifically, now we want to consider the conformal defects and conformal boundaries. So how do we obtain them? So we start from the 3D Ising CFT with a space-time dimension as O d plus 1, 1. So to get a line defect, the simplest way is to take a line out of the space-time and polarize it In other words, we add the lowest Z2 odd operator sigma and take the sigma and integrate it along the line. And in the IR, it will flow to the line defect CFT with a smaller conformal group SO2, 1 times SOD plus 1 longitudinal. The line defect, the defect CFTs is known to have rich property. For example, like the bulk, there can be primary operators that lives on the defect. And because the conformal symmetry is much smaller, many correlators that is forbidden by the bulk and conformal symmetry is now allowed. For example, there can be a bulk to a one-point function of bulk primaries, and there can be a bulk to defect two-point correlators. They are power laws, and the coefficient in front of the power law is a universal number called the bulk to defect bulk to defect OPEs. And for boundaries, by taking a semi-infinite space and set different boundary conditions on the boundary, we can get different boundary CFTs with a conformal symmetry SOD, 1. There can also be boundary primaries and bulk to boundary 1-point and 2-point correlators. So using the fuzzy sphere, we have obtained a ton of information about the magnetic line defect and various Ising conformal boundaries. Of course, we don't have time to introduce all of them. So let me outline some important points. So the first point is the RG irreversibility. Speaking of which, the most famous example is the C theorem in 2D bulk CFTs, which asserts that there exists a C function that is non-increasing along the RG and its value equal to the central charge at CFT fixed points. Such theorem determines some fundamental structure of the RG flow. And in 3D and 4D bulk CFTs, later people found that there is also such monotonic quantities called the F function and the A function. It's not only on the conformal line defects, and people have also found that there is a G function that is non-increasing along the RG, which is defined as the ratio between the partition functions of the defect CFTs and the corresponding bulk CFTs. And we can similarly define the boundary central charge, which is RG monotonic in the conformal boundaries through its response to the space-time curvature. Such quantities are very, very important as they are fingerprints of the defect CFTs or the boundary CFTs, but they are very difficult to calculate non-perturbatively. So using the fuzzy sphere, we have obtained the first non-perturbative results of the G function of the Ising magnetic line defect and the boundary central charge of different kinds of Ising boundaries. And the value has proven to agree very well with later conformal bootstrap results. And the second significant question is the symmetry breaking on defect. Namely, can there be a stable spontaneous symmetry breaking on the conformal defects or on the Ising magnetic line defect? We know that for an independent 1D system, there cannot be spontaneous symmetry breaking. But what if it is coupled to a bulk? This comes down to the problem of proliferation of the domain walls and the relevance of the domain wall operator. If the domain wall operator is relevant, it has Slane dimension less than 1, then the domain walls can proliferate and the symmetry breaking is unstable. In the language of conformal defects, this translates into the defect changing operators, which is we take two semi-infinite long defects polarized towards different spin direction. For example, the upper half at spin up and the lower half at spin down, and drawing them at one point. In this way, we get the defect changing operator. And similarly, if the upper half is polarized towards spin up and the lower half has nothing, this corresponds to an endpoint of the defect or the defect creation operator. On the fuzzy sphere, through the radial quantization, it is easy to realize a conformal defect just by polarizing the north pole and the south pole of the sphere. Similarly, if we only polarize the north pole, this corresponds to the defect creation operator. And if we polarize the north pole and south pole towards different direction, this corresponds to the defect changing operator. And we can calculate their scaling dimensions by similar technique of state operator correspondence. And we find that the defect changing operator is relevant, which means the symmetry breaking is unstable on the Ising magnetic line defect. And if we take the overlap between the ground state of different defect configurations, we can obtain the overlap can tell us many information, including this G function. It is nothing else than the ratio of the overlap 0, 0 with +0 and ++ with +0. This gives us the first non-perturbative result of the G function. And for the boundaries, there exist many different conformal boundaries for the Ising CFT. For example, if you explicitly break Z2 symmetry, it is called the normal boundary. And if you preserve explicitly the Z2 symmetry and tune a boundary interaction, you can obtain the ordinary surface CFT, where the Z2 symmetry is preserved, and an extraordinary surface CFT, where the Z2 symmetry is spontaneously broken. So on the fuzzy sphere, these boundary CFTs can be realized by polarizing half of the sphere and keep the degree of freedom on the, for example, keep the degree of freedom on the north half and polarize the south half. If we polarize it towards its direction, then it corresponds to the ordinary, and if we polarize it towards Z direction, then it corresponds to the normal conformal boundary. So, as a brief summary, we have shown in the simplest case of the Ising CFTs that the fuzzy sphere is a powerful tool to study the conformal defects and the conformal boundaries. And we have obtained a wealth of information about both theories. And in the future, we wish to use the fuzzy sphere to further study more defects. For example, the monodromy or spin impurity in the Ising or Owen-Wilson-Fisher and the Wilson lines in the gauge theories, and more boundaries. We can go through the whole phase diagram, or even study the boundary coupled to 2D CFTs. So finally, I would like to acknowledge my collaborators, my supervisor, Yingchen He, and David Gayotto, and Zheng Zhou from Perimeter Institute, and Wei Zhu and Liangdong Hu from Westlake University. And the talk today are mainly based on the following 4 papers. So as a concluding remark, since the proposal of fuzzy sphere, the study of 3D CFT has been revolutionized. Many theories that people cannot study before, now people have proper tools. many quantities that people cannot calculate before, and now now they can calculate. It's not only the 4 words that I mentioned today. For example, the deconfined criticality, the SPN theories, and the easing conformal defects and boundaries. There are a lot of other other exciting things going on, and our journey will our quest will be ongoing. For example, can we study more on the gauge theories? Can we study, for example, the fermionic and bosonic QED? Can we tackle the conformal window problem? Can we study more transimus matter theories? Not only the gauge theories, can we study more other CFTs? For example, can we study the CFTs with fermionic operator content or even the supersymmetric CFTs? Can we directly study the complex CFTs and the most promising candidate being the deconfined criticality and the 3-state Potts model? Can we say more about the defects? For example, can we go through the phase diagram of the Ising or Owen-Wilson-Fisher boundaries? Can we study some more significant non-perturbative defects? For example, the monodromy and Wilson line. And can we further improve our technique? Can we further improve the quality of the slaying dimensions we calculate by the conformal perturbation theory? Can we give a systematic error estimation of those quantities we calculate? And we are trying to do benchmarks of all those things. All those technical improvements we are trying on Gaussian or Wilson-Fisher theories. Finally, there are more fundamental questions. For example, how to do anomaly matching on the fuzzy sphere? How do we interpret the properties of the orbital space? For example, the entanglement and the fluctuation in the orbital space. And the final question, are there any hidden structure that helps us to understand the 3D CFTs? All these ongoing questions comes down to how we can exploit and understand the magic of the fuzzy sphere. Finally, to facilitate everyone from doing numerics on the fuzzy sphere, we have developed this open source Julia package, fuzzified, which you can check on this website. Using this, you can produce almost all of the existing results on the fuzzy sphere. We have provided a list of 25 examples, and they can finish running within, for example, 1 minute, and within the code length of, say, 100 or 50 lines. So that's the end of my talk. Thank you.
Thank you, Zheng, for the very interesting and exciting talk. Any further questions?
Yeah, can I ask a very naive question? So it seems like this fuzzy sphere technique rely on this conformal symmetry structure, right? So
Yes.
I wonder, like, what is the key algebraic structure that conformal field theory provided such that you can apply this fuzzy sphere approach? Like the question the reason I ask this question is because there might be some other type of critical behavior that's not really described by conformal field theory, but maybe some other algebraic structure that could emerge. So is it so what is the key that this fuzzy sphere approach will work?
So from what I understand, the reason why the fuzzy sphere works so well for the 3D CFTs is, first, it preserves the full SO3 symmetry, which makes the flow from the UV to the IR much shorter, which makes the final size effect much smaller.
Mm-hmm.
The second is the conformal flatness of the manifold, which enables us to make use of the properties of the CFTs on the flat space-time, for example, the state-output correspondence.
Mm-hmm.
I'm not so sure about the algebraic structure on the fuzzy sphere.
I see. Yeah, but I just think it might be very interesting to see, to explore the potential possibility of this fuzzy sphere approach beyond the framework of conformal theory. But maybe it is not yet really explored. Yeah. Yeah, thanks.
Any other questions?
Thank you. Yes.
Any other questions? I have a question. So when you mentioned the study of a boundary, you said on the fuzzy sphere, what one has to do is to make one half of the sphere different from the other half.
Yes.
My question is, do you have to divide the whole sphere into half and half? Can one side be 1/3 and the other be 2/3 and so on?
And in this case, the geometry will correspond to a cone.
If it's 1/3 and 2/3.
Yes. It will correspond to a cone. Because you see the dilatation actually it shrinks and enlarges the sphere, which makes the 1/3 cut into a cone.
Is there anything interesting for the cone?
Yes, there should be interesting things. But so far we are not sure how to study them. So I think the scenario is quite similar to a cusp. That is to say, you join two defects at an angle. So so a defect in a shape of a cone shall be something that is quite interesting.
And
for example, we can study the cone operators, that is the operator living at the tip of the cone. We can also study the correlation functions of the bulk operators in the cone CFT.
And it's also experimentally relevant because cones can easily exist. I can easily cut a cone.
Yeah.
Also, how good is the fuzzy sphere at calculating the 4-point functions?
And there has been work calculating the 4-point functions. This work, I believe. And so far, I think it is possible to calculate an arbitrary 4-point function. So the 4-point function comes down to if you put one at 0 and another at infinite, it comes down to acting at two local operators at two different time slices or at the same time slice. This I think is possible by some by some DMRG technique that admits time evolution.
Okay. My last question is about the previous part. You said suppose you want to determine the SPs, determine which gauge theory the SP model corresponds to. You think the large N calculation is hard. Why do you think the large N calculation in this particular case is harder than the other large N calculations?
I vaguely remember that I cannot say too much about it because for some I haven't yet done a very thorough survey, but I think I vaguely remember that for some cases, there is not a very well-defined large n limit. So in some cases, the large n cannot quite make the resumation of diagrams much simpler. I vaguely remember that this thing happens to some of the SP engineering.
In those cases, I guess the gauge group is large, but the flavor is not too large. Is it the case?
That's true. That's true.
Okay. Thank you. Any other questions?
Excuse me.
Yes.
Yeah, I have a following question. So, following the Professor Liu Jun. So I want to ask, so if we want to handle a large N system, so do we need to simulate or calculate from numerical aspect? So do we need a more large system size or even more large point on fuzzy sphere?
So actually, the large N calculation does not the cost does not grow so fastly in the Monte Carlo calculation.
Yeah.
So Monte Carlo is actually very good at large N calculations of this kind.
Yes.
Because what you need to do is just power on the partition function.
Okay. Okay.
But actually, for example, the ED and DMRG calculations, the large N goes very bad.
Okay. Thank you.
For example, for the DMRG, the local dimension actually grows very fast with the N.
Oh, so okay. Okay. So what's the maximum system size you have calculated in your before experience?
So for example, for the eSIM, we can do up to 18 orbitals or 20 if your computer is good enough. For the SP and for the SP2 theory, we can do up to 10 or 11 orbitals. That is with 4 flavors. And for SP3, what we can get is 7 orbitals.
Okay. Yes, thank you. Thank you.
Maybe one last question. I asked this before, let me just confirm. Regarding the difference between different nano levels, I think previously you said if I define one Hamiltonian in any of the nano levels, then there's another Hamiltonian in another nano level, such that the matrix elements of these two Hamiltonians are the same.
Yes.
Is this discussed in detail in some paper, or I should just be able to work it out, or assign it as a homework problem to quantum mechanics class?
The thing is, if you look at the orbital space, you forget the sphere. If you forget the sphere exists, you only look at, for example, four fermion terms such as like CM1 dagger, CM2 dagger, CM3, CM4. Terms like that doesn't have any knowledge of the real space profile.
But the coupling coefficients have. Oh, I see. Although the coupling coefficients have some structures coming from the wave functions of the nano level states, you mean I can always tune the other parameters in the Hamiltonian to make them the same? Is this the point?
Yes, more or less.
Uh-huh.
The thing, and the other thing is you can you can make a construction completely in the orbital space.
Mhm.
That is, have nothing to do with the real space.
I see. Mhm. Okay.
Yeah. I think there will be some discussion about the model construction of ours that involves only the orbital space profile. I think in the appendix of the SPM paper
Mhm.
and also in the 2503 paper.
Mhm. I see. Thank you.
Thank you.
Any other questions? Okay, if not, let's thank Zheng again for the very interesting and exciting talk. Thank you. Now I will close the Zoom. Bye.
Bye bye. Thank you. Bye bye.